This is a neat one because normally you find projections onto, if you're talking about two dimensions, onto like the x or y axis, or in three dimensions you talk about the xy plane, or the yz plane, right? That's sort of like when you do level curves, you are tracing them out projections on the one plane. Right? That's why it's easier than actually trying to make the whole thing come together. 87 says find the projection of this on the plane 3x plus 2y minus z equals 0. So this is sort of like, the extension of this would be sort of like finding the projection of, like the one level easier problem would be finding the projection of 2, 3 on some arbitrary, like 1, negative 3. Right? And we've actually done a problem like that before. So we have like 2, 3 and 1, negative 3, and I want to find the projection of this that's parallel to this, and the projection of this that's perpendicular to that, right? So that's really what they're asking for. They're saying find the projection of this position vector on this specific plane. Now the nice thing is, what's the normal to this, and what does that mean about it?
3, 2, negative 1.
Yeah, so the normal to this is 3, 2, negative 1. So how do you think you can find the orthogonal? Well, I don't want to find the orthogonal, but if you had to, you could find the orthogonal projection by just doing that projecting onto this, right? Cool? No, not cool, but very semi-cool, not so good.
Yeah, but this vector of the plane is orthogonal.
I like it,
plane.
cool. I like
yeah,
it.
so we have to find a plane that's, we have to find a vector that's parallel to the plane and finding the projection.
There's two kind of ways to approach this problem. This kind of leads you down one path, that I think should be a quicker way to do the problem. Another way to do the problem is, this guy is really difficult to graph, so you can't really get a feel for how that guy hovers over this plane. Right, so you have a vector, you have a position vector 2, 3, negative 4, and then there's a plane that I'm trying to project it onto. Right? So I actually had to do a test problem where I said project this onto the xy plane. Of course, xy plane is always going to be easier to work with because it's set up really nice with my coordinate axes, but this is very similar to that problem also, right? So if you could figure out, number one, if you could figure out possibly where these meet, that might help you out in a way. And then you can see the projection of this onto that plane a little bit easier. That might help you find the point where they meet. Anybody else try this problem yet? This is one that I assigned?
That's not part of it.
It's not?
Yeah, it's
Well, you
not
just
part
asked.
of
Okay, good.
Yeah, it's not.
Gotcha. Right. But that's why this is a little bit harder than normal, because it's not one of my basic, just finding a projection of a vector onto another vector. So one way to do this is to, where would these two meet, for example? I mean, this is a position vector, but it's, let me see, it's not easy to draw. So 2, 3, negative 4. So it would be 2, 3, negative 4 roughly. So that's that. And then I've got this plane here, and 3, 2, negative 1 is the normal to that plane. Right? And they tell you, cool, that's all they do. And it's actually the plane. Can you tell me something else about this plane? I mean, that's the normal to the plane. What else is kind of nice about this plane? What point does it go through? That's an awesome point for something to go through. Doesn't it go through the origin? Right? 0, 0, 0 works because it's equal to 0. So this plane, if you can draw 3, 2, negative 1, so 3, 2, negative 1, this plane is going to be orthogonal to that going through this, right? So you kind of draw a right angle. So there's a plane there. Of course, extending in all directions, right? Okay. So it'd be, I'm not going to try to put that up there also, right? But what I'm trying to say is the shortcut is if you know the orthogonal projection, how do you get the other piece of it? What's the shortcut? If you know one projection, your orthogonal projection or the parallel, how do you get the other one?
By subtraction.
By subtraction, right? That would be the first thing that came to my mind, is just to do it that way, right? That's the quickest way, because that's the easiest thing to get a hold of. Because what you're having trouble with right now is what vector do I use in that infinite vector place, that whole plane, right? And it's difficult to tell where that vector hovers over that plane. Now, so I don't know if you guys remember the problem I gave you in the test when I said find the projection of this on the xy plane. That was an easy one because I knew it was right over the x-axis. I just had to drop it right on top of the x-axis. But if it's somewhere else out, I got to figure out the whole problem. Then is the problem is just what line in that plane is it over, right? Okay, cool. Maybe.
So we can find that line by finding the intersection between two planes. And that line is actually, and then kind of do the regular projection.
Well, if you have this plane, the plane described, so the other way to do this is to take the plane described
By this one.
by this, and
We
that's
can
how many
intersect.
planes do that though? How many planes are described by this?
A lot.
A lot, yeah. Right?
Because I need a point for that.
But you want, and that's getting ahead of us, that's getting to regions we haven't gotten to, because then I want like a tangential plane to another plane. I want a plane that goes perfectly through another plane, and it's not easy to get.
Okay.
But to me, the quickest way is the way I just said. Right. All right. I don't want to spend too much time on that one because it's not actually homework. I didn't want it. Are there any other questions from
76.
homework? 76. Oh, cool. So this one says, find the points where the planes and curves intersect. So I want this plane and this line and this is t greater than 0, obviously. And I want to know where those two meet. So what's a good way to write this that would be more useful? Yeah, exactly. You can break it down into more of a parametric form. X equals 1, y equals root t, z equals. And then where do you think you can go from there? Plug it in. So these, where they intersect, you should kind of go, no matter what the hell they look like, you should sort of go, thank God. Because all I got to do is figure out how to use one set of information. How to use this information in there. And normally the best way is just direct substitution. Right? Directly substitute the information they give me here, directly into there.
Because it's intersecting. So there are x and y.
They have to be
the
both
same.
true, exactly. So it's the same old thing from algebra. How do you solve linear, a system of linear equations? Or actually a system of equations, period. The one way that works most of the time, most directly, is just substitution, right? Especially here. Trying to eliminate something is not the easiest thing in the world to do here, right? I'd much rather substitute, yeah. And you get a nice little equation in T that you can solve. Yeah, cool. Okay. It's not going to be monster easy, but it's going to be relatively easy. Yeah. So those kind of problems, you really should be like, oh, thank God, it's just an intersection problem. I just have to figure out how to plug one set of stuff into the other thing. Okay. Any other questions from homework? Okay, cool. Well, maybe cool. We'll see. All right. Last time we did section 12.2, which is not the easiest section in the world to do, and that's a caveat that I threw out there very early on in my discussion. What's most important? I already went over what's most important to try to get out of this. And level curves definitely are a lot easier. In fact, level curves, I often think about it. You guys ever seen those lanterns, those that you can hang out in the yard and you kind of open them up and they become this big ball, right? They have a little lantern. You can put a little, you know what I'm talking about? You can collapse them. So So I think of level curves as me just taking the whole ugly thing, whatever the hell it looks like, and just collapsing it. Right? That's what I think of when I see level curves. And you can just uncollapse it in your head somehow. You need a little help, because if I just give you something like this, it's not really enough to uncollapse it. But you can imagine maybe this thing is kind of like going like this up. So it's kind of going out as it goes up. Right? Do you see how that, if this is higher than this, then it's going out as it goes up. The information I'm missing from a level curve is this up or down from the one before it? What's the key difference between each of these lines I just drew, each of those curves I just drew? What do they represent? Where do they come from? What would I want to write next to each one of them to keep myself straight? Z equals something. So that is different levels, right? So I've collapsed all the different levels into one plane. So if you can kind of uncollapse them in your head, if I had next to this Z equal -1, Z equals 0, Z equal 1, then it is exactly like I said. It's going up and out as it goes up levels. Right? As you go up on the Z axis, it's kind of going out like that and up. I don't know if you guys can kind of see what I'm saying. I don't know if this is really useful here. Right? Like you're trying to choke somebody. Okay. Maybe. And the last little thing I want to say, some of you guys might have seen something like this before, but look on page 797. This is kind of cool. Actually, I'm going to try something here too. We always get trouble when we try to go beyond 3 dimensions, obviously. It's hard enough to draw 3-dimensionally. Not only is it difficult, it's impossible just about to draw 4-dimensionally unless you kind of, not really cheat, but you're creative. So on page 797, you can see, for example, figure 1236A is kind of a representation of the heart. Those of you who are taking any biology at all know that the heart does not necessarily look like that. So this is obviously a rough estimate of what the heart looks like. But the different colors represents different electrical activity at each location on the heart. Right? The one next to it, part B, let's see, now if you look up here, 1236B, the dependent variable is the switching speed in a circuit. So if any guys are computer geeks, you know exactly what that means. If you're not, it's just exactly that, it's just the speed of how quickly it can do something. And they're not really very explanatory on that one. Let me see if I can make this come up here. Okay, cool. That's for later. I just realized that I really personally hate PowerPoint, but I figure I might have to embrace it, considering I can't draw worth anything.
Take an art class.
I did, actually. Yeah. I think I'm I can paint. Don't get me wrong, I can paint. If you try to make me draw, no. Painting, yes.
Don't you have to learn how to draw before you can paint?
No. Where's my painters? Is that true?
No.
Not necessarily, no.
Oh.
Especially if you're impressionistic. Which I don't necessarily mean to be, but I am. Let me see something real quick. I want to show you this slide, just in case you don't have the book. Blah, 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 blah. There. So in case you don't have the book, there's a representation of the heart. And the different colors represent electrical activity. So normally, of course, and you've seen this kind of stuff on brain scans. So the brain itself is 3-dimensional. So you've already got 3 dimensions used up. The only thing you can use then to kind of show a 4th dimension, a 4th piece of data, is different colors or different colors about it. So this could be low level activity. This could be high level. So if you know where there should be electrical activity and there isn't, you go, oh crap, something's wrong there. Right? Maybe there's too much activity somewhere. That's kind of cool. So to go beyond 3 dimensions is difficult to picture, but that's actually a creative way to do it. They are showing 4 pieces of data up there. 3 dimensions plus electrical activity dimension, right? So that's a 4-dimensional image, believe it or not. 1 dimension is color, but oh well, it's awesome. Okay. So in your homework, I don't think I assigned too many sketches by hand. And I think I said that last time. Let me know if you disagree with that statement. I'll keep track of who said that. But you just got to jump in there and try it out. One thing I want you guys to realize that I didn't really make a big point of is if you read the book, they talk about contour curves. They don't really make a big point of this either. But on page 792, a contour curve is actually where I just slice it, and I don't put it all on one plane. So it's sort of like the first step. I slice it. I'll show you this here. Oh, where'd it go? There I am. Here. So these are contour curves. See those green rings? Those are actually sitting in the image. And then when I put them all on one plane, they become level curves. So just in case they make the distinction in the homework somewhere, that's the distinction. Contour curves are really just cutting it in 3 dimensions. Level curves are just smacking them all into 1 dimension, right? Here's a good question I saw somewhere. Could you ever have level curves that intersect? Could they ever meet?
No.
Why?
Yeah, of course.
Because the function will have 2 values for the same point.
Exactly. You can't have more than one value. It's got to be a function that we're talking about here, right? So you can't have more than one output for any given input.
Exactly.
Yeah. And these are, and why are they called level curves? Why do you think they're called level curves?
Different levels.
Wow, I like it. Let me take both words and put it inside. But I mean, that's basically it, right? I mean, it's where I would be able to walk on a flat surface. And if I wanted to, so if I'm going in circles, I'm fine. But if the minute I want to go this way or that way, I've got to go up or down to get to the next level, up or down. Cool. Yeah.
But what if there's like, it's a straight like cliff, just drop off? Wouldn't the circle down here be the same? Would it overlap?
No. Because, well, for one thing it would, but then would that be a function? You'd have a lot of points, a lot of different outputs for the same input then, right? So this idea really only works
It's
for...
kind of like having like a vertical line that's really...
Exactly. So what's the analogy in 3 dimensions with determining if this is a function? It still does a vertical line test, believe it or not. So now vertical lines are hitting this thing everywhere, all over the damn place, not just in one plane. It's got to be in all planes, right? Any line drawn parallel to the z-axis can only intersect this thing once, and that's exactly related to every input can only have one output. Right? And I always say that sounds like Highlander to me when I teach that. There can be only one. There's a few more people that get that reference in here. I like that. Okay. So I just want to make that distinction real quick, but level curves should definitely be a lot easier than traces and trying to put all the traces together on one thing. So I want you guys to try it out as well as you can, do the best you can, and try to make it clear your work, what you're trying to do. And that'll be probably fine. So today we're going to get into section 12.3. And then 12.4. That's my plan for today. We'll see what happens. So, remind me in 2 dimensions, in our good old y equals f of x notation, what did it take for there to be a limit to exist at some point?
Left and right.
I like it. So the limit from the left has to match up with the limit from the right. Does it have to exist there?
No.
I like it. If it did exist there, that would be requirements for continuity. Which still doesn't really say that derivative exists there yet. You could have a sharp curve like that. Continuity's fine, derivative sucks. So how would that look like? What would happen if I just added another dimension to this? Everything we've done so far, when I added another dimension, it didn't really get that bad. I don't know if you guys agree, but it actually didn't. A lot of analogies go directly between 2 dimensions and 3. When you add another dimension here, though, What are my inputs now when I go to a function of two variables? If I have z equals f of x1, which I'm giving you the answer there. What are my inputs now? They're points, right? In some region. So we talked about that the other day. I've got some region where every point goes to an output, and then I get this weird little thing that hovers right over the region that I can use. It's really exactly the same as this. Here, am I allowed to use A? No. So, but everything else has this thing hovering over all the x's that I'm allowed to use. It's the same thing in 3 dimensions now. It's just going to be a blanket or something. So the weird thing is, aren't these two different paths here? If I call that path 1 and path 2, I'm taking two different paths, and in order for that limit to exist, those paths have to agree. How many paths can I have now in 3 dimensions?
4.
So here's like an example of a domain. Right? Now let's say I have a point P. And let's say the point is 1, 2. How many ways is there to get to that point? And this is a weird question, and the answer is an infinite number. Well, why would that be true? I mean, what does it look like to get to that point? Because here, there's really only 2 ways to do it, from this side or that side, and that's it. You got it. That's how you can go here, right? Now, see if I got another color here. I can go there, 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 right? There's a lot of different ways to get to that point. And along each of these, here's what I really want you guys to understand. What I just drew, is that the function?
No.
This here, this whole thing. That's the area of points that I can use. Where's a function then? Above it or below it, or you could even intersect it, right? But let's just assume it's like right here. Well, here's the surface that I'm talking about. So this point here goes to there. This point goes to there, and so forth. Right? So as I let my inputs, just like we did here, as I let my inputs approach that point from all directions, they better all agree on where that thing is going. Just like here. Or else what's true at that point, if they don't agree?
It's not a function.
No, it's still a function.
There's no limit.
There's no limit. The limit just doesn't exist there yet. Cool. So this is still a function here, of course, right?
No.
That's definitely a function, but does the limit exist at point B?
Yes.
At input B?
No.
Does the limit exist?
Yes, but only for this side.
Come on now.
It depends if you're going from
The
the left
limit
or
does not
the
exist because the two directions don't match. Right?
Okay.
Don't give me depending on, no. The limit existing requires both directions to be the same. I could say, does the limit exist from the right? Yeah. Does the limit exist from the left? Yeah.
Okay.
Does the limit exist? No. They don't agree. Right? It's difficult to see. And I'm going to try to show you some images up here that I'm hoping will make it easier. To see how you could have multiple possible limits just because you're coming at it from a different direction. Right? This is kind of a weird top thing to kind of keep in your head. So I'm going to attempt to show you how this could possibly work. In fact, let me before I get into the problems of this, let's do a couple that work beautifully, and then we'll talk about where would the problems come in. So, for example, recall, what was the limit as x goes to 4 of x squared minus 7?
1? No. 8.
Yes. So, of course, you just plug a 4 in. Why do you know you're allowed to plug a 4 in?
Polynomial. It's
Because it's
continuous.
polynomial.
It's a polynomial, so yeah, it's continuous everywhere, which means the limits must exist everywhere, right? Even more than that, is there a problem at 4 in there? Is there a problem at 4? No. That's the way I try to teach it when I first teach limits is, if there's a problem, you've got to approach it a different way. If there's no problem, meaning that 4 can go in and doesn't freak anybody out, you just attack it directly. Another little thing from the past. Who remembers how to do something like this here? Oh no, Jeff. You want to do this way. Let me make this, sorry. All right. Closer. I want it to be a problem. Let's see. Yeah, that's fine. That's fine. Good. There's a problem. Yeah. Yeah, so again, how do you do that? Multiply the conjugate, and then eventually you're going to get something canceled. So when you multiply by the conjugate of this, plus 1. All right, so you're going to see similar things to this in this section too. So you get x minus 2 times this over x minus 1 minus 1. So of course those cancel. And I don't want to forget my limit. And then so that's fine. What does that actually come out to be?
Two.
What's the matter?
When you have 2 on the bottom, you get a 0.
No, the bottom just cancels with the top, right there. Bottom.
Oh, yeah.
So now you plug a 2 in, square root of 1 is 1 plus 1 is 2. Okay. So that's what I mean by, no, there was absolutely no problem here. Here there is a problem that I took care of. So limits are easy when there's either no problem or I can easily take care of the problem. And the problem is very often division by 0. Right? As you've learned, there are actually other problems that can happen, but that's the one that we're going to focus on. So what do you guys think about, let's see, let me just show you what this is going to look like. So start us off nice. So it used to be letting the input go to a value. Still I want to do that. I want to let, it's the same thing. I want the input to go to a value, but the input is now a point. So I have to let that input point go towards some point, specific point. Is there any trouble with putting 1, 2 in there? No. So you just put 1, 2 in there, right? Incredible, right? So 1 squared minus 2 plus 2, 1. I like it. So just be careful about putting the right value in the right place. Believe it or not, when you get to this level, you only forget to look into that. So you're going to see a lot of these that have no problem whatsoever. Either they have no problem or it's really easy to take care of the problem, right? You either have to multiply with a conjugate or you have to factor the top and cancel the bottom out because then the problem goes away, right? It's when the problem won't go away, which is very obviously when you have a problem because the damn thing won't go away. So for example, let me see which one I want to do. Here we go. If I have a problem, here we go. This is on page 804, by the way. Example 3. When the problem won't go away, more than likely, the limit won't exist. But I still have to prove it. Just because I can't figure out how to make the problem go away doesn't mean it can't. Doesn't mean that there's still some limit. Right? So here's the weird thing. Here's the thing I really want you guys to get. My inputs for this. What could I plug in there? What's my domain?
Except 0. 0 for x, 0 for y.
Everything except that damn point that I want to go towards, of course, right? And that only makes sense. We always want to investigate the weird spots. And the way to do that is to take a limit, because then I get really close to the weird spot and never get right on top of it. But there's nothing I can really do here, is there? You foil the top out, I can't directly cancel anything, that just sucks. Right? So what could I do then? I have a feeling that this does not exist, that there's no limit here, because I can't remove the problem directly. I want to find a path that if I follow it, and then another path if I follow it, they come to two different places. In 3 dimensions, it's harder, of course, but it's the same idea as it was in 2 dimensions. So here, let me just show you how this kind of works. One path I could take, and again, my allowable thing is everything except 0, 0. So I can go to that point any way I want to. I'm going to show you kind of like what the book does, and then I'll show you what makes the most sense, period. Right? So let me do something a little more general first. I can approach that along any line that I want to. For example, I can approach it along the line y equals x, right? If I really wanted to. Of course I could. Because what's really going on here, I really want you guys to understand. I want to take x, y to 0, 0. Does it matter who gets there first or how quickly one gets there? No, all I want is x, y to go to 0, 0. Right? So if I do it in a manner where y equals x, so I put 2, 2 in, I put 1, 1 in, you can imagine doing those tables like you had to way back when you did Calc 1. How did you first do limits? 0.1, 0.01, 0.001, right? So you went crazy. Is there a pattern? You can do the same thing here, but let's do it more generally. If I let y equal x, what happens to this? Simplify that if I let y equal x. Take a minute and try to simplify this if I let y equal x. I'll help you out on what this is going to look like. You're so helpful, Jeff. Simplify what that will look like now.
Is that 2x?
It's 2. 4x squared over 2x squared?
Now let's see what we get. We get x plus x is 2x squared is 4x squared, right? On the top? Over 2x squared, which is 2, because the x squareds go away, right? Now, that's kind of cool. You guys start to see what I mean? You could use any damn thing you want to. You can make it y equal x squared, y equal the square root of 1 minus x. Weird shit, right? As long as it actually exists at this point that you want to go towards, right? Obviously, I couldn't use y equals 1 over x as an approach because 1 over x has its own problem. So I don't want to do that to myself, right? So what's another path I could take besides y equals x? Let's maybe keep it linear. There's no reason to make it, but I could. There's nothing wrong with doing that. If I do, let's do it. I haven't even thought about it. If you want to do y equals x squared.
That's just.
Aw. That would be kind of disgusting, right? You still do it. What would you get then if you did y equals x squared? So here's y equals x. This is the path. If I choose the path to be y equals x squared. And sure enough, if x goes to 0, so does y. So overall, I'm still going towards the point 0, 0. That's the idea. So y equals x squared, what happens up here?
X squared plus 2x.
X squared plus x4. Right?
So x plus 2x cubed.
And it's the limit as x goes to 0. Will this come out to something that I can actually work with? I don't know.
Yes.
It will?
I think so.
So it's the x squared plus 2x cubed plus x4. I think that still has the same problems as before. Right? You guys kind of with me? Is that a good path to use?
No.
No. We don't have to use that path. Right? What's a better path, maybe that's still linear?
Y equals 2x.
All right, cool. Y equals 2x. This tells me. So we're still working with this stuff. So I want to approach it y equals 2x. Just so you know, I mean, this is what I was worried about when I took this class a million years ago. You're not going to be totally left alone. They're going to tell you if it's non-existent, so you know when to try these paths out, right? I only try these paths out if I can't eliminate the problem directly by conjugates or factoring and canceling. If I can't do that, then I try a few paths. It's like a counterexample, and you should be able to get it pretty quickly. find a counterexample. This path goes here, this path goes here, they don't agree, doesn't work, no limit. So what happens when y equals 2x? You get 3x squared up here, right? Over x squared plus 4. Right to 2x, yeah. 4x squared. So you get 9x squared over 5x squared. What's that limit? 9/5.
Easy.
There you go. Right? So if I approach it along y equals x, it goes to 2. If I approach it along y equals 2x, it goes to 9/5. Right? And what you got to keep in mind, this is the hard part. This is what I want to show you up on the screen here, is if I'm going along the y equals 2x, don't those have their own inputs? I mean their own outputs, right? So y equals x, the outputs are kind of going towards 2. But over here, y equals 2x, those outputs are going towards 9/5. That's still fine. It's still a function. It just means that I'm dropping off from one to the other one. But they don't agree. So does this limit exist? No, this limit does not exist because they don't agree from 2 different sides. And now I have an infinite number of freaking sides to go to, right? Here's the paths that I always use, unless something in the problem tells me I can't. What's the easiest paths to take? Instead of going along some y equal mx path to 0, 0, I would just take the path x equals 0, oops, y equals 0 or x equals 0, right? Just go along one of the axes. In fact, do both of them. Maybe if they're different, you're done. And of course, they're the easiest things to do, aren't they? So if I take this limit, oops, take that limit there. Let me write it again here real quick. X plus y squared, or x squared plus y squared. Now if I take the path y equals 0. What do you get here? And that's really just taking the path of how can I go to 0, 0? Can't I go to 0, 0, 5, 0, 4, 0, 3, 0, 2, 0? Won't that eventually get to 0, 0? Of course. 0.10, 0.010, if I really want to step in really small increments. Same idea as before. Well, what do you get when you plug a 0 in for y? Yeah, x squared over x squared, which is 1. What about the path x equals 0? Now this will suck, it's not really helpful at all. Too bad. Y equals 0. So, I'm sorry, limit is y goes to 0, so when x is 0, what do I get? Y squared, that's still 1, that sucks. But the nice thing is, didn't I do this one already? That was 2. And here I got 1. So they don't agree, right? So I'd always kind of do these two first, because if they're different, I'm done. If they're not, then I got to do another one. I got to pick like a 2x or a 3x or whatever I feel like, right? So let me try to show you an image of this happening and see if this helps us out a little bit. Just got to remember where that guy is. Let's see. If you do x equal to 0 and y equal to 0, and you get 2 different things, who asked that question? If you get 2 different things, that's all I want to show. It's just like showing going from the left is different from going from the right. Isn't that enough to show that the limit doesn't exist there? So if I approach this along one path, x equals 0, right down the y-axis, and then y equals 0 along the x-axis, and those go to 2 different things, one is down here, the other is up here, then obviously it doesn't work. It doesn't exist there. They have to agree from both directions that you choose. So if I would have done these 2 first, they came out the same, I would have had to do another one. And I would have done y equals, what did we choose here? Y equals x. Right? That's the next easiest thing to choose. Right? And then if that comes out different, I'm done. I just got to find that counterexample. And again, in the book, they will tell you these don't exist. Show me why. Right? You just got to find the counterexamples. Yeah.
So if you did those 2 and then they were the same, and then you did the 3rd one, it was also the same, does that mean it does exist, or do you have to try another one?
No. Thankfully, it's normally pretty quick to find two that are different. And if you're doing 2x, 3x, 4x, and they're all coming out the same, then try some negatives, right? Maybe that'll do something.
Okay.
Normally, you can see something from the function that tells you what to plug in there. Most of the time, it's quick.
Okay.
These two sometimes will come out the same, and you just do one more, and you should find it pretty quickly.
Okay.
Yeah, okay. You can't prove that it exists this way, obviously, right? Because again, how many passes did it take? An infinite number. You have to show it works for all of them. So, let's see. Oh, I want the one that I can manipulate. There we go, cool. So this guy, here's the function. 3xy squared over x equals y4. And what they're doing is they're actually going along a path, x equals my squared. They're going along a parabolic path. And that m then, they're doing more than one path at a time, whatever m is. So if you plug this in, x equal my squared, you can kind of see why they did that. If I make x equal my squared, this will match up then, right? Those will be like terms then. That'll be y to the fourth at the end, plus another y to the fourth. It makes it easier to kind of look at the bottom. So if I actually do that work, we'll try something different on this too than what they did. Why does my approach, and I can see this right off the bat, that my approach, approaching it from x equals 0, y equals 0, why will those be, of course, the same? If I approach along x equals 0 and I approach along y equals 0, they're both going to be 0 here, right? I know the numerator's going to be 0, so the whole thing's 0. But then I just have to do one more and see what it comes out. So then I would choose y equals 2x maybe or something. Here they chose to go along here just because then these would be like terms. Okay, so that's the kind of thing you can look for. What's going to end up with a nice thing you can kind of maybe cancel a bunch of stuff out. And on the top you're going to end up with y4, right? So then those will be able to cancel out just like they did for us over there. So when you plug that in, you get limit blah 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 3m y4 over m squared y4 plus y4. So those y4s all cancel out, and that's why they got this guy. So the nice thing is, since my answer to the limit is a function of this m, which could be anything, that right there tells me what? The limit does exist or doesn't? Can't. Because if I make m1, the limit is 3/2. If I make m2, the this limit gives me 6 over 5. There's two paths that don't agree already. So look what happens up here. Notice something. I want you guys to see something. Do you see right here how there's a gap there? I don't know if you guys can see that well enough. Oh, how can I zoom in on this thing? Oh. Sweet, thank you. Control, scroll, troll. I like that. All right, I think you guys can see that now. See that gap in there? Right? So at 0, 0, it actually has no value. That gap goes all the way down. Right? And it can't have a value because at 0, 0, this thing is undefined. Right? What are we doing so far? There can't possibly be a value there. But there can be a lot of what it looks like it's approaching. Up here it looks like it approaches something. Let me turn this thing around. This one's kind of cool because I can control what m is. So there's what the parabola is. They actually show me the, like the trace, but the level curve down here. And here's the actual contour up here, right? So if I approach it along x equal to 1 y squared, so I approach it x equal y squared, then all my outputs live up here. And so as I approach it, it's going to, of course, go to this point. Right? Now we saw when I had to turn around that it actually doesn't exist there. There's a gap there. But that's what it looks like it's approaching. How are we doing so far? The minute I change m, if I go along -1, If I come from the back, of course, then they're going to be down here. Right, so you can automatically see, and this is one of those ugly things we tried to do the other day, with these parabolic traces, but back here it all lives down here, so of course they're going to approach negative something for an output, right? So right there's two paths that don't work. If I approach 0, 0 from up here, it looks like it's approaching this z-score. From down here, it looks like it's approaching this z-score. So that's exactly the same as in just a nice two-dimensional thing. They don't match up, right? And you can actually kind of see, it's almost like making a two-dimensional right here. This does not match up with that. They're both actually open circles here, right? Cool. That's the idea. That's all there is to it. So the really nice thing, the thing I would be worried about is that if I were you, if they left it totally vague, just, we don't know if these limits exist, check them out. That would so suck. Because then you could trap yourself. If you didn't see how to factor something out or something, you could be there all day picking different paths, and they're all going to work because there's something you could have done to make it easy, right? So thanks God how they actually break it up into sections. They say, whoa, let's not do this. Let me see if I missed anything here, and then we'll try this quiz thing out.
Break time.
Is it? Holy crap. Alright. That's my problem though. I mean, maybe not for you. For you guys, I'm sure time is different. Alright, let's take a break. Let's take like, come back at 40 after.
Jeff, have you ever seen the movie Scanners?
The movie Scanner? Yes.
You're gonna go do that?
That's what I should bring out video clip and put it up and be like, this is what we feel like.
I'm getting better. Man, I don't want to go get it. Oh, I know. If I just touch one of those, I don't feel so.
Really? Yeah.
Really? You just gonna sit in here? Don't be lame. We need fresh air. Come with me, I'll go get food. Come on. Come on. In this top. Yeah, but like a little bit.
I went to the early lesson. I don't know why. I was really tired.
I think playing Battlefield was really kind of screaming at at least level 1. Yeah, I woke up really
My little sister texted me because she went to Party City and you were working. Party City's hard. I was like, I know, my friend works there. And I was like, I'm not gonna do it. And my mom was like, yeah, mom's with it.
Yeah.
But she was like, yeah, Party City's hard. I was like, no. Really like super busy.
Two people up front.
There was like on Sunday it's really busy football and stuff. And we just schedule like in the morning to work inside and one person to drive. So it's 2 people to do like 20 games. And the next person's gonna come into like 4:30. One time I had to open for a turn. I haven't been working Sundays.
I like well, I work normally I open to be open at 6.
close at 11. Closing at the hospital. Like they'll get like they close at 11, but you won't get home until like 12.
Good. How was the last chapter?